We're constantly hearing that training these massive AI models requires, well, equally massive amounts of data. The more data, the smarter the AI gets, right?
Prevailing wisdom, yeah.
Well, get this. A recent study has sort of turned that idea on its head. Researchers found that sometimes just a single, carefully chosen math problem can boost a large language model's performance as much as training it on literally thousands of examples.
That's, yeah, pretty wild.
Isn't it?
It really makes you rethink how these models learn, fundamentally.
Yeah.
So today we're diving into some fascinating research that looks at exactly this. How efficiently large language models can learn complex reasoning,
Right.
specifically for math problems using reinforcement learning. And the core question we're kind of tackling is, what's the absolute minimum amount of data you actually need to significantly improve an LLM's ability to reason?
Exactly. And, this isn't just some abstract academic thing. This deep dive offers you a direct path to understanding some truly cutting-edge AI research. We're going to unpack how these models develop their problem-solving skills and highlight the surprisingly large impact that a tiny bit of very focused training data can have. So hopefully you can ditch that feeling of information overload and maybe prepare for some real aha moments as we explore what makes these complex systems tick.
Yeah, definitely. And our roadmap for this exploration is this research paper. It's titled Reinforcement Learning for Reasoning in Large Language Models with One Training Example.
Catchy.
Well, it gets straight to the point. We'll be extracting the key findings and exploring what this really efficient learning approach might suggest for the future of AI.
Okay, so our mission today is pretty simple then. Take this fascinating research, make it clear, engaging, and directly relevant to your understanding of how AI learns and reasons. All right, let's jump right in. What was the central discovery, this one-shot RLVR thing the paper talks about?
Right, so the paper introduces this concept called reinforcement learning with verifiable reward, or RLVR for short.
Okay.
When we're talking about training LLMs to solve math problems, this usually just means giving the model a really straightforward reward signal. Basically, it gets a 1 if the final answer is correct and a 0 if it's wrong. Simple binary feedback.
Makes sense. Correct or incorrect?
Exactly.
Yeah.
Now, what's so compelling, the real kicker, is when they applied this using an incredibly small amount of training data, literally just one single problem. One. They called this one-shot RLVR.
Just one problem. That sounds, I don't know, almost too simple to actually work. What happened when they tried it?
Well, the outcomes were really quite remarkable. When they used this one-shot RLVR on a base model, they used one called Qwen 2.5 Math 1.5b, using just that single carefully selected math problem.
Yeah.
Its performance on standard math tests just improved dramatically. Like, for instance, on the Med 500 benchmark, the accuracy soared from 36.0% all the way up to 73.6%.
Whoa, hang on. From 36 to over 73%? With one example, that's an unbelievable jump. That's hard to wrap my head around.
It is quite striking, isn't it?
Yeah.
And what makes this even more significant is how this one-shot performance stacked up against training with much larger data sets.
Okay, yeah. How did it compare?
They compared it to training on like a 1,200 example set called DeepScaler and even the full 7,500 example math training set.
Right, the standard approach.
And in many instances, the model trained on just one or maybe two well-chosen examples performed just as well, and sometimes even a little bit better.
You're kidding me. So thousands of data points versus one or two?
Yeah.
And you get similar, maybe even better results. That really challenges the whole more data is always better idea.
It certainly does. And this wasn't just, a fluke with one specific model or setup. They saw similar substantial improvements across different language models, too.
Oh, really? Like which ones?
They mentioned Qwen 2.5 Math 7b, Llama 3.23b Instruct, DeepSeek R1 to still Qwen 1.5b, and also using different reinforcement learning algorithms like GRPO and PPO.
Okay, so it seems pretty robust then. It's a more general effect.
Yeah, that's what it suggests.
Okay, this is where it gets really interesting for me. You mentioned these carefully chosen examples. Were they just any old math problems? What made them so special?
That's a great question. The paper highlights two specific examples. They label them 1 and 13 that turned out to be particularly effective in this one-shot RLVR approach.
Pi 1 and Pi 13. Got it. What were they like?
So example 1 was an algebra problem, but it had a physics context. And interestingly, the official answer provided in the dataset was actually slightly off. It was around 12.8 when the more precise answer was closer to 12.7.
Huh, okay. A slight inaccuracy in
Okay.
13.
That one was a geometry problem, and it had a precise solution. No ambiguity there.
Right. So what was it about these two that actually led to such big gains? Was it the type of problem, the slight error?
Well, here's the really surprising part. The base model, even before any of this one-shot RLVR training, was already quite close to solving these problems correctly.
Oh, really?
Yeah, especially for one. The base model frequently generated outputs that were very close to the more precise answer of about 12.7. And for 13, too, the base model often got it right, or very nearly right initially.
So wait, it wasn't about teaching the model something entirely new from scratch then. It was more like activating something or fine-tuning something it already kind of knew.
That's a very insightful way to put it. The researchers themselves propose that one-shot RLVR might be primarily about effectively activating existing reasoning abilities that are already latent within the large language model.
Great abilities. Okay.
It's as if the model already understands most of the necessary steps, maybe, but needs that single targeted reinforcement signal to consistently put them together and arrive at the accurate final answer.
That makes a lot of sense, actually. So, okay, they train on this one example, and I assume the accuracy on that specific problem probably hits 100% pretty quickly, right? Is that the end of the story?
Not at all. This is where another really fascinating phenomenon comes into play, something they call post-saturation generalization.
Post-saturation. Okay, what's that?
What's so intriguing is that even after the model achieves 100% accuracy on that single training example, so it's solving that one problem perfectly every single time.
Right, it's mastered it.
Exactly. Even after that point, its performance on completely new, unseen test problems continues to improve significantly. And this goes on for many more training steps.
Hold on, it's mastered the training problem, but it's still getting better at other different problems. How does that even work? It sounds counterintuitive. It's like becoming an expert at, I don't know, one specific piano piece, and somehow that makes you a better overall musician, even on pieces you haven't practiced as much.
It does seem that way, yeah. The researchers observed that actual overfitting on the single training example, where the model starts generating kind of nonsensical or irrelevant outputs, sometimes even in different languages, just for that one problem.
Right, when it gets too focused.
That overfitting occurred really late in the training process. We're talking after many hundreds, sometimes even thousands, of additional training steps on that single example.
Wow, okay.
And crucially, even when this overfitting started to happen for the training problem, the model's performance on the unseen test set remained strong. The reasoning steps it showed for those test problems still looked normal and logical.
That's wild. So it's almost like it needs to hyper-focus on that one specific example, maybe even to the point of overfitting it slightly, to really solidify the underlying reasoning process. And that process then becomes more broadly applicable.
It's a nuanced idea, but yeah, that might be part of it. They contrast this with what often happens when you train on multiple examples. In those cases, you might see performance on new, unseen problems kind of level off, or maybe even start to drop before the model has completely mastered all the training examples.
Right, the classic generalization gap.
Exactly. But with one-shot RLVR, this very concentrated training on just a single problem seems to allow for this extended period where generalization to new challenges keeps improving.
Okay, so it works for that one specific problem, helps it generalize better to other problems. But what about different types of math? If you train it on, say, an algebra problem like 1, does it only get better at algebra? Or does it help with geometry, too?
That's another key finding.
Yeah.
The improvement isn't domain-specific. One-shot RLVR leads to performance boosts across different mathematical domains. Algebra, geometry, number theory, pre-calculus, you name it.
Really?
Yeah, it's not just improving performance within the specific area of the single training example.
Okay, that's great. So it suggests the learning is deeper, more fundamental. It's not just memorizing tricks for one type of problem.
Precisely. It suggests the reasoning skills being activated are more foundational than just, say, mastering algebraic manipulation.
Got it. But were those initial high-impact examples, like 1 and 13, the only ones that work this well? What happens if you just picked a random math problem for the one-shot training?
This is another really surprising part. The researchers actually tested this extensively. They found that one-shot RLVR was remarkably effective for nearly all the math examples in their full data set.
Nearly all. Wow.
Yeah, most individual examples, when used for this single-shot training, resulted in at least a 30% improvement on that Match 500 benchmark.
A 30% jump from most single examples.
That's what they found. And this held true pretty much regardless of how much the model's accuracy on that particular problem varied during its initial pre-training phase, or how difficult the problem seemed to be for the base model.
Huh.
The only real exceptions were cases where the problem had a genuinely incorrect answer in the dataset, or if it was so incredibly hard that the base model couldn't even get close enough to receive any positive reward signal during training. If it never gets it right, reinforcement learning can't really work.
Right, you need some signal to learn from. But okay, so it wasn't just those two magic examples, 1 and 13. Almost any reasonably solvable problem had the potential to trigger this significant boost.
That seems to be the implication, yes. And maybe even more counterintuitively, they found that the specific mathematical domain of the training example, like whether it was algebra or geometry, didn't strongly predict its ability to improve performance in the same domain on the test set.
Wait, say that again? Training on geometry didn't necessarily make it best at geometry.
Exactly. Training on a geometry problem might, in some cases, lead to a bigger improvement in algebra performance compared to training on a different geometry problem.
Okay, that is weird. It really suggests the skills being honed are super general reasoning abilities, not tied to specific math topics.
It points strongly in that direction, yeah. It's
Okay.
less about the topic and more about, perhaps, the structure of the reasoning required.
This is getting really deep now. Did they notice any changes in how the model was actually solving the problems? Like the steps it took after this one-shot training?
Yes, they did look into that. One interesting observation was related to self-reflection. After one-shot RLVR, the model started using terms like rethink, recheck, or recalculate more often in their generated reasoning steps when tackling the test problems.
So interesting. So it was becoming like more cautious or thorough, almost like a student consciously double-checking their work.
That's a good analogy. This increase in self-reflective terms also seemed to correlate with the training progression.
And did they see other changes?
They also noticed an increase in the overall length of the model's responses and something called entropy loss during the one-shot RLVR process.
Entropy loss. What does that signify?
Higher entropy loss generally suggests that the model is exploring a wider, more diverse range of potential ways to solve the problems. It's not just sticking to one predictable path, but considering more possibilities.
Ah, okay. So it's trying out more diverse solution paths, becoming less deterministic, and maybe that's part of why it generalizes better to new problems.
That seems to be a plausible connection, yes. More exploration might lead to discovering more robust reasoning strategies.
Right. So to dig into that a bit more, did they look at why this RL approach was working so well? You mentioned the algorithm, GRPO. Did they break down its components?
They did. They looked closely at the GRPO loss function they were using for the reinforcement learning. Broadly, it has a few key parts. There's the policy gradient, something called Kale divergence for regularization, and this entropy term we just mentioned.
Okay, can you unpack those a bit? What role did each play in this one-shot magic?
Sure. So there are ablation studies where they systematically remove or change parts of the process to see the effect, indicated that the policy gradient loss was the primary driver behind the performance improvements in one-shot RLVR.
The policy gradient, that's the part that directly encourages actions leading to rewards, right?
Exactly. Think of it as the core reinforcement signal saying, do more of whatever led to that correct answer. And interestingly, they found this improvement wasn't heavily dependent on other common factors, like weight decay, which is a form of regularization often linked to a different learning phenomenon called grokking.
Ah, right. Grokking is that sudden jump in generalization after apparent memorization. So this is different.
It appears to be a distinct mechanism, primarily driven by that direct reward signal from the policy gradient, applied intensely to that one example.
So it wasn't just some lucky side effect of the training setup. The reinforcement signal from that single problem was genuinely doing the heavy lifting.
That's what the evidence suggests. And they also found that actively encouraging the model to explore more diverse outputs by incorporating that entropy loss term with an appropriately chosen coefficient.
The exploration part again.
Right. That further boosted the performance. It reinforces the idea that just getting the right answer isn't enough. Encouraging exploration of how to get there is also really important for generalization. The entropy term essentially rewards the model for trying out different reasoning pathways.
And you mentioned something really intriguing earlier, that even just the entropy loss on its own had a positive effect, without any reward.
Yes, that was a particularly striking finding. They ran an experiment where they only applied the entropy loss, basically, just encouraging the model to be less predictable and explore more without giving it any feedback on whether its final answers were correct or not.
And what happened?
Even that alone, just pushing for exploration without reward, significantly improved performance. It gave about a 27% boost on the Match 500 benchmark.
Wow, just telling it to explore helped it solve math problems better.
It seems so. It suggests that simply prompting the model to explore a wider range of possible reasoning steps can independently enhance its underlying problem-solving abilities, separate from the reward signal itself.
That's incredible. So, okay, pulling all this together, what are the main implications here? What does this tell us about AI and where things might be heading?
Well, I think one of the most important takeaways is that these large language models, even the base versions, seem to possess a substantial amount of unpacked reasoning potential. They already know more than they might show initially.
Right, the latent abilities you mentioned.
Exactly. And one-shot RLVR seems to be a surprisingly efficient method for unlocking or activating these capabilities using a minimal amount of very targeted data.
Which has big implications for training, I guess.
Huge implications for how we approach data selection and curation in reinforcement learning, potentially. Instead of maybe just focusing on creating massive, diverse data sets, we might get better results, or at least more efficient results, by carefully identifying and using individual examples that have this high-impact potential.
So it's maybe a shift towards prioritizing the quality and the specific characteristics of training data over just the sheer volume.
Precisely. It suggests that developing methods to evaluate the potential impact of individual training examples could lead to much more efficient data selection strategies down the line.
Makes sense.
But, there's still plenty of open questions. We don't yet fully understand the exact mechanisms that make one-shot RLVR and this post-saturation generalization so effective.
Right.
Concepts like implicit regularization, this idea that the training process itself, like using stochastic gradient descent, inherently guides the model towards simpler, more generalizable solutions, might be playing a role here. But how exactly is still a bit fuzzy.
Implicit regularization.
Yeah, it definitely sounds like another deep dive for another time.
Huh, indeed. And the importance of exploration seems really crucial. The researchers highlighted that finding even better ways to promote diverse outputs, maybe beyond just using a simple entropy loss term, could be a really promising direction for future work.
Because the entropy loss isn't perfect. Well, its effectiveness can be quite sensitive to choosing the right coefficient, the right weighting. Maybe there are other, more robust ways to encourage useful exploration.
Gotcha. And this research focused specifically on math problems. Do you think this one-shot approach could work in other areas? Like, could you teach coding or creative writing this way?
That's a great question and seems like a natural next step for investigation. The paper itself briefly touches on the potential for extending one-shot RLVR to other domains beyond math. It would certainly be fascinating to see if similar effects hold for, say, logical reasoning puzzles or code generation or other complex tasks.
Yeah, definitely.
Oh, and one other small point they mentioned was about label robustness. They found that slight inaccuracies in the training label, like that one example where the answer was slightly off, didn't significantly hurt performance.
Okay, so it can handle a little noise.
Yeah, but significantly wrong labels, especially if they're somehow easy for the model to memorize or overfit to, could actually be worse than labels that are completely wrong, but maybe harder to guess or latch onto.
Interesting nuance. Okay, so to try and recap the big things here, we've learned that counterintuitively, a single math problem can be incredibly effective for training AI reasoning, like shockingly effective.
Right, the one-shot power.
And that models can keep getting better at general problem solving, even long after they've perfectly mastered that one training problem, this post-saturation generalization, and that encouraging the model to explore different ways of thinking, maybe through things like entropy loss, is really key to unlocking this potential.
Exactly. Policy gradient drives it, exploration enhances it.
That's pretty revolutionary stuff compared to how we usually think about training these models.
It really is. This research genuinely challenges our fundamental assumptions about needing these vast quantities of data for sophisticated AI. It gives us a compelling glimpse into the latent abilities that might be hiding within existing models.
Untapped potential.
Untapped potential, exactly. And it suggests the exciting possibility of developing much more efficient, much more precisely targeted training methods in the future. Less brute force, maybe more finesse.
Okay, so here's a thought then, something for you, the listener, to really chew on. If a single, well-chosen example can unlock such significant reasoning capabilities, what are the fundamental characteristics that make certain examples high impact? What makes 1 or 13 so potent?
That's the million-dollar question, isn't it?
It really is, and maybe thinking bigger. What other cognitive abilities in LLMs, creativity, planning, common sense, might we be able to unlock using similarly data-efficient techniques? It truly makes you wonder about the hidden power contained within what might seem like the smallest, most insignificant pieces of data.
That's a really insightful question to ponder as we wrap up. Thank you for joining us on this deep dive into this fascinating research.
Yeah, thanks for listening and for contemplating with us the surprising power that can reside within just a single data point.